Hello, Zach here. So I'm going to talk about STEM EDS tomographic reconstruction. This is a talk, and a lot of the data is pertinent. My plan is to kind of go through the basics from this talk, but also to walk you through doing an actual reconstruction using the software, and also the acquisition. I have some video footage of using the TitanX microscope at National Center for Electron Microscopy, showing you how to actually acquire these data sets. The first thing to mention is that it's available on this, within this project here at GitHub. So if we just go there, then this is the project, and all the code for doing tomographic reconstruction is here. You can also email me, and if you have any questions. This software should work on Windows, Mac, and Linux. I've done reconstructions on all three platforms. Within this project, if you look under the openNCEM Pi directory and then under data, you see L2083. This obtuse number is a number assigned by Johnson Space Center for this particle, which is a piece of cometary dust. It was captured in the upper atmosphere by a stratospheric plane by NASA. And this is what that sample looks like. And I use it as a demo set for doing tomographic reconstruction. So these are some crystals here, and in EDS you see those same crystals. And the reconstruction ultimately looks like this. Now this particular sample is ideal for a demo because it's somewhat thin, so you can see there are places, for example, here and here, you actually can get a clear shot through a single phase. But of course, the reason you use tomography is often for something like this, where you cannot get a clear shot through a single phase. I'm going to assume that you are already familiar with tomography principles in general. I'm not going to cover that here. I'm just going to cover specifically how you do EDS tomography and the differences from normal tomography. So the largest difference that you're dealing with compared to imaging tomography, for example, using high-angle annular dark field, for normal tomography with imaging, you just want to get as many images at as many tilts as you can, and over as wide a tilt, a variation of tilt angles as you can. So if you can get hundreds of images from all 360 degrees around a sample, that's the best. And when you're doing EDS tomography, that's not the best. And the reason is because you are limited in terms of how many counts you can get out of a sample before your electron beam alters the sample. So what you want to do is take fewer acquisitions, but get enough signal in each acquisition that you get an image that is recognizable. This is, for example, an image from one tilt. This is a magnesium K alpha X-ray signal from that sample. And if you want to do a reconstruction of where the magnesium atoms are, you want to have a single image look something like this. You still want to get as wide a range of tilt angles as possible. So if you can get, plus 60 to minus 60 degrees on a TEM, you're doing well. And however, instead of getting an acquisition at every degree or even half a degree like you might with a HOTF, you want to do something like every 5 degrees. And I've even done every 10 degrees. 5 degrees seems to be a nice sweet spot, at least for my samples. We're then going to use binning in order to get the noise level down to what we need. Okay. If you're interested in these slides, you can also ask me for them. And then this now gets into the tomographic reconstruction. So before we go there, let's talk about how to do the acquisition in practical terms.
This is the TitanX TEM at the National Center for Electron Microscopy here in the Lawrence Berkeley National Lab, Berkeley, California. I have a sample loaded. This is from an interplanetary dust particle. This is a comet sample that was retrieved from a NASA ER2 airplane from the stratosphere. This is a hummingbird holder right here. And it provides a very nice, very tiny holder for the grid so that you can get to high tilt angles for tomography. Inside, we have here a 4-element Bruker SDD, which has a solid angle of 0.7 steradians. So one thing you want to do is, once you've got your sample loaded, here it's at 0 tilt, you want to make sure that you can get to as wide a range of tilt as you can. In this case, I can get from plus 65 degrees to negative 65 degrees. So I'm covering 130 degrees total, which gives wonderful tomography. You want to set your beam currents and so forth appropriately. In this case, I'm running about 1/6 of a nanoamp, which I'm at 80 keV. And that means that I get a lot of EDS counts, and my sample survives throughout the entire run, which takes, in this case, it's about an hour and a half for the EDS map, because I use 2 minutes at each tilt from negative 65 to plus 65 every 5 degrees. And so what I normally do in this case is I might move to negative 65 degrees first. So I'm negative 30, negative 40, negative 50, negative 60. Now you want to go a little past 65. So in this case, I'm now at 67. The reason for that is that you want to be moving in one direction the whole time. So starting here at 67 degrees, I'm going to type in 65 degrees. And of course, I have told this to only move alpha and beta, so it won't try and move X, Y, and Z, which would be a nightmare. And then, so negative 65. Bang. So now we won't have a whole bunch of hysteresis and so forth happening while the sample is moving between tilts. So then I use the stage controller to bring this back to the middle. And then you need to refocus it. If your eccentric focus is perfect, then this all becomes easier. So the better you can set your eccentric characteristics, the better off you are. I usually put a end position up here, so when I stop the scanning, then the beam will go up here and not burn my sample. And then you would start a new map. I have drift correction on, and I find I use 512 by 512 typically. You could use a smaller raster if you wanted. And here I'm using 20 keV range. And here I have the acquisition set for 120 seconds. Depending on what map, I'll play with that a little bit. In this case, I have a nice wide range of tilt angles, and I'm getting in the, quite a few counts. So 36,000 counts per second on the object. So that's enough counts to get a pretty good map within 2 minutes. So if I let this run here for a little bit, you can see what's happening. All right, so the map just finished. So then I save it. At some point, we'd like to automate all this. So this is just done from a control program, but for now, it's still hand done. So you type -65.bcf and save that Bruker file. And then you're going to use the Python scripts later to read that out. And there it is in our directory. So now you're going to start the viewing again, and then you can go to -60. There we go. As you can tell, I don't have perfect eccentric characters, so I have to adjust this a little bit, put that back in the middle, and refocus. And then you can turn the search off again and start your new map. Now, in this case, this is an isolated object, which means you can use center of mass in order to align the stack relatively well. In other cases, you'll also notice there's not a single nice fiducial. Like sometimes you'll have a bright object or something roughly in the middle. And when you do have a nice fiducial, what I will do is drop a crosshair onto the image, something like this, right on that object. And then when I realign, use the stage to bring the object back to the middle after each change in tilt, I make sure that fiducial is always on that point. That greatly aids your alignment of the stack later, if you can do that.
Okay, so we are back at the computer now. I'm going to switch to the testing demo set. So first we open a browser. We're going to go to the GitHub site. So github.com, Ercius, ERCIUS, openNCEM. That is the GitHub site. And now we're going to open up a terminal. I'm going to increase the font a lot. That just makes it easier to see on a video. All right, so the first thing I'm going to do is clone this repository. And that puts it in a directory called openNCEM. Additionally, I want to point out, if you just Google Gainsforth EDS Tomo, then I have a short tomography, I guess. Then you can see a short conference abstract, which gives a link to this code, as well as a quick explanation. All right, the next thing we're going to need to do, I'm going to make a fresh install of Python so that you can see everything that you need to do to set it up. In this case, I'm using Anaconda, which you can also use a virtual environment if you wish. Anaconda is from Continuum.io. It's a Python framework. So the advantage of Anaconda is just it's very handy. So I can say conda, create a new environment. I'm going to call this EDS Tomo, and it's going to be Python 3.7. And this is making a fresh Python for me. Conda activate EDS Tomo. Now I'm in my new Python. And you can see that it's got its own directory and everything. And it does not have much installed. So import numpy as np, and that fails because numpy is not installed. All right, now what we want to do is we want to install the openNCEM package. And so if we come down here and we look at install instructions, it's pip install ncempy EDS Tomo. And so this actually should be in quotes. And And this is going to download a bunch of packages that are needed not only by NCEM but also specifically for EDS Tomo. And this can take a little bit. In addition, there's an optional package called FFTW, and it's not necessary to install it, but I will do so anyway because it speeds up the tomographic reconstruction. Because this installation step takes a bit, I'm going to fast forward through this for the video. Okay, it's all installed. Now I'm going to install FFT. One of the advantages of using Conda is that you don't have to download PyFFTW and then use GNU C compiler to make the package and all this jazz. You just install it and it magically appears. Okay, now we're going to go into the openNCEM project. And I'm going to open File Explorer here so that you can see what our basic structure is. So within the NCEM project, there's two directories relative, which are important for EDS Tomo. One is obviously the EDS Tomo directory itself, and that has the source code here. And then the data directory contains this sample, and this long obtuse number is a number assigned by Johnson Space Center for this. This is also a cometary dust particle, just like the other one that we had earlier in the video. And in here, I have two different IPython notebooks to do the processing step by step, and we're going to walk through that. So I'll put this down in the corner, and we can come back to that in a bit. So Jupyter Notebook. The first thing we want to do is go to the notebooks. And the first step is convert Bruker to EMD. So this set was acquired on a Bruker instrument, as you saw. Within the input directory here, here are the BCF files saved from the TEM. BCF is the Bruker special format. And then if I open up the Python notebook, I'm going to make the font bigger. Then for the most part, I'm going to let you read the code. It should be pretty self-explanatory, but I'm going to try and describe the bigger picture aspects of it. So there's three main modules within the NCEM EDS Tomo module. We've got, these are submodules, pre-process, post-process, and Bruker. Bruker is, its job is to translate the data from the Bruker format into the EMD format. And the EMD format is defined by the National Center for Electron Microscopy, EMD format. If you Google NCEM EMD format, then you can find, I think, EMD data sets, electron microscopy data sets, and this describes the format. We use this for many types of data sets, not just tomography, but also 4D, STEM, and so forth. So once it's in this standard format, then you can pre-process the data, do your reconstruction, and then there's some post-processing you can do as well. You need to set up the directories where the Bruker files are and where to put the EMD file when it's done and what to name it. We're going to return to signal names in a bit. And the first step is just to read all those in, and then it creates a big data cube. So it recognizes here that there are 21 tilts and 200 by 56 by 256 pixels in this particular set. Each of these have to have exactly the same number of pixels, obviously. In the case of the EDS data cube, there's an additional direction which is the 2048 energy channels per pixel. Now, in the case of this particular data set, I've set up the conversion notebook, which is under the second directory, reconstruct EDS Tomo, to use the output directory. So it's going to look up one directory, then down convert Bruker to EMD, and down output. So if you're using your own data set, you might be wise to simply mirror this directory structure and use the existing notebooks. But if not, then you just need to set up your own paths. Within reconstruct EDS Tomo, there are a few files. In order to be able to see the notebook without having to run it, I've saved it as an HTML complete with the images which describe the process. So in this directory, there are a few ping images which are part of that HTML. There's also this tomviz alignments.json, which we're going to get into in a sec, and many elements 2bin and 4bin.cxe, and those are for using ChimeraX, which we will also get into shortly. So I'm going to open up the notebook now. And again, you can read the code. It's pretty straightforward. Here, these directories are set up to the structure I just described. And I'm also going to now explain signal names. So I'm using what's called the ELAM database. It's published by NIST. If you look for ELAM database NIST, then you can go to National Institutes of Standards, and you will find it here. Download the ELAM compilation down here. Okay, and this is a database which has a record for all of the different fluorescence lines for all the elements, the absorption energies and cross sections, all that jazz. And so I'm using it in order to extract signals from the EDS data cube. In the case of ALK, for instance, it's going to choose the weighted mean of the aluminum K alpha and K beta lines. They're very close together, so EDS does not resolve them as separate. But in the case of calcium, it's going to choose the calcium K alpha line as the signal. Similarly, the Bruker data files also had the HOTF signal, so there's a special case for extracting HOTF. You can use whatever elements, whatever lines are pertinent to your system, and it will extract all of those, and we can do reconstruction of all of them. And of course, the first step is to read the signals out of the EMD file. So there's that large cube in the EMD file, and now it's going to produce subcubes for each of these signals. All right, that took a little while. So it's now done. There's a lot of number crunching involved in that. Here, for aluminum K alpha plus beta, for instance, it used the mean, and then it extracted a window of values, which is derived from basically this Fano computation. So based on the energy of that fluorescence line, it then chose bins above and below. So basically it took all the energy bins between 193 and 200 in that cube. Okay, so now that that is all complete, the next step is normalization. Now, normally if you are doing a HOTF stack, for instance, then as you tilt to higher angles, say you might be looking at some nanoparticle on a substrate, and that substrate will become effectively thicker as you tilt to higher angles. And usually that you would normalize out thickness variations as a function of tilt. In the case of EDS, though, what you have is kind of an opposite effect. So in fact, I'll show you in the keynote. Here, you have your tomo holder and you have the EDS detectors at, in our case, the takeoff angle is 18 degrees. So when the tomography holder is tilted to plus or minus 18 degrees, you have the lowest solid angle for detection of X-rays by the EDS detector. And so you get the fewest counts. When your tomography holder is at a very high tilt, like 60 degrees or like 90 degrees, then all of a sudden, all of the EDS detectors are clearly visible straight to the sample, and there's no absorption of the photons within the sample. So therefore, you have to normalize the overall intensity as a function of your tilt angle. So here, the best signal comes at minus 50 and plus 50 degrees. The worst signal is actually plus minus 18, although in this particular instance, it's a little more than that, probably because of the thickness geometry of the sample holder or the fib section that this was on. And then you get an intermediate value at 0 tilt. 0 tilt is actually not the best angle for getting a lot of counts. Interesting, huh? All right, so in order to normalize it, I have a pre-processing signal, pre-process normalized signals, and then you have to tell it what element you want to normalize to. So normally you want to choose an element which is high enough energy so that there's no self-absorption in the sample, right? Photons that are coming out of the sample are not going to be absorbed by the sample on the way out to the EDS detector. At the same time, you want a lot of counts. So you need an abundant element with a relatively high energy. In addition, normalization image fraction here is saying to just use the center half of the image. So it's going to discard a quarter off the right and left side, and a quarter off the top, and a quarter off the bottom. And sometimes that's useful when you have material coming into the field of view as you tilt. So you don't want more material coming in for your normalization signal. All right, so let's pre-process it. That happens very fast. Bam. All it's doing is multiplying each of the frames by the appropriate factor to make them all have the same intensity overall. And then it's going to write out this data into a bunch of TIFF files. So output directory was defined above, up here, output directory. In this case, I'm doing for binning, which, by the way, the binning was defined in the extract signals over here. Binning equals 4. That just reduces the number of the amount of noise in each pixel. And so that put it into a directory here called output for bin, unaligned because it's the raw data. And so you have a stack for each element. So let's take a look at this. So here is the hot-F stack. As we tilt it, this is what was recorded. If you look at the magnesium K, notice it's smaller because of the for binning. And that is what you see. So the first thing we need to do is align that stack. You can align it using ImageJ or Fiji. ImageJ has a really good alignment. Plug-in, registration, stack reg, choose translation, and go. And you can see it's very well aligned. And then in this case, I'm doing a alignment with TomVis as well. And so I wanted to show you how that works as in addition. Usually I do the alignment using the hot-F signal, and then my software will apply the same alignment after factoring in the whatever the binning was to the other signals. So first thing to do when you open TomVis is to open the data, which is going to be the HOTF signal. Voila. And then before you can do alignment, oh, here we go. We can do alignment right away. So there's a couple ways to do it. One is back and forth between the images. So here we're comparing image 11 and 10, or I prefer to do it this way, where you click here and you use the arrow key. So left arrow, left arrow, left arrow, etc. And you just move the images until they're in alignment like this. So right there's about the best. And then you hit S. Notice A or S here. And now I'm on the 12th frame and comparing it with the 11th frame. You do a similar thing, and so on. And then when you are done, you would save alignments, and that would go into the unaligned directory here. You'd say tomviz alignment.json. All right, now this file has a format which is basically the alignment in pixels. How much does it have to shift each frame? So I only adjusted 2 frames. So it will shift the 11th frame negative 16 pixels in X and plus 1 pixel in Y, negative 15 in X and plus 2 in Y for the 12th frame, and so on. And you need to do this for every frame. And I've already done that. So rather than make you sit here and watch while I do that, which would be rather boring, I'm going to instead use my previous alignment, which is here. So I copy that, and then I come over here and I'm going to paste it. Oh, and it should be tomviz alignments with a plural. All right, now we come back here, and here we're saying which file to use and where the path to it is. And so it's going to preprocess, read tomviz translations, and that makes this array. And then it's going to apply those translations to all the signals. It doesn't take very long. Notice that it recognizes the HOTF. It applies the translation directly, but for all the EDS signals, it only applies 1/4 of the translation because the binning was 4. All right, the next step, and if you keep an eye over here, you'll see it. And now we run it, and that's pretty quick. It makes this directory called aligned, and it has all of the aligned stacks over here now. So let's look at MGK as an example. And you can see that it is wobbling just a little bit, but only by 1 pixel, with which, considering the noise that you're going to have in the reconstruction anyway, is quite acceptable. There's also a MGK aligned.npy, which is short for numpy. That's a data format for Python that the GENFIRE reconstruction routine uses. And then there's a shell script for running this on our compute cluster that we have here at the National Center for Electron Microscopy. You could, of course, modify the code if you like, if you'd rather have it make a different kind of a shell script. But the shell script only has 1 line that really matters. Open with, let's open this in the editor. Oh, it's trying to open it in the terminals. Okay, it's this last line here. Python do GENFIRE pi, and then you have to give it the element. And so included in this directory is do GENFIRE.py. And this is just a Python script, basically, which loads the GENFIRE module. and then makes a call to it with default parameters that work really well for reconstructing EDS tomographic data sets. And you're welcome to play with those once you get a little handiness with this whole routine. So if we just take that line there, open this up, and I'll make this bigger. So we are in the align directory, and I'm going to say Python do GENFIRE MGK. Then this is GENFIRE running, and this is a reconstruction algorithm which is really wonderful in terms of handling noisy data sets. The reason why it's so powerful is because it applies constraints in an iterative process. So it's converting into Fourier space and then back into real space. And in both spaces, it applies constraints to get rid of noise from the transformations. And so it does a much better job than the, I shouldn't probably say old school methods of CERT and ART. Those both work really well, but GENFIRE works much better, especially for EDS tomographic data sets. So you see here, it's actually already half done. I'll just let you sit it out for a sec. And then I will be ready to show you what we get. So MGK is here, and it's going to create new files, which it outputs as soon as it's done. 90, 95, and done. So here, these three files are just text files describing how the reconstruction went. And then mgk reconstruction.mrc is a file that it outputs. So you can actually see how the reconstruction looks. So this is coming at it from the side. You might, for example, slice this from the left and come at it this way, and you can see it better there. I'll just project this so you can see it. So that's looking through the entire reconstructed stack. All right. I also want to show you Python do GENFIRE for HOTF, because you're going to need to say -O1. Typically, this is the case, and the reason for that comes from the do GENFIRE code. I have here command line arguments. Actually, I will just show you. If I don't give it arguments, it tells you what the command line arguments should be. So you have -N for how many iterations you want. It defaults to 100. -O for the oversampling ratio. The HOTF cube is usually too big to fit in your RAM unless you have 128 megs of RAM or something like that. So therefore, you want to say HOTF -O1, so it's not oversampling. You only have to do this with the HOTF signal, not the other signals. All right, so now I'm going to pause the video. I'm going to go do all the signals, and then we will continue. Right, we're on the home stretch now. So we've reconstructed all of the signals. And so we want to read in each of these cubes, and we're going to just trim the cubes. So I want to show you how this works. This line reads in the MRC file, in this case, mgk reconstruction.mrc. And then you set up some crop bounds, and it crops it. So I'm going to copy that and paste it. And I'm going to set this to go from 0 to 1, which means no cropping, so that you have comparison. Output file directory output for bin. Right. Now, after it's aligned, if you, it's a good idea to change that to reconstructed. And if you wanted, you could copy the aligned directory into reconstructed instead. But here you go. And this is what your cube looks like. And as happens with all reconstructions, you always get this kind of a halo around your object, this cylinder, and that's just a consequence of the fact that you're not fully sampling all the space. And when you reconstruct, then this is an artifact that occurs. So you're usually wise to crop. So for example, here's the x-axis, and in my case, the sample only goes from about here to here, which is 0.4 to 0.6 roughly. So if we just crop that from 0.4 to 0.6, then you can see it's a lot nicer. That's not even a very aggressive crop. And you would have to do this according to your sample, whatever your sample looks like. So here, for the purposes of this demo, these are the crop boundaries I chose, and that's what you get. So we now apply that to all the signals. Boom, it's cropped them all, and you get a bunch of these new MRC files, CK reconstruction cropped, CAKA reconstruction cropped, and so on. And now we can load those into ChimeraX. So I have here script files for ChimeraX. So this is a ChimeraX is a tomograph viewing software, and it has a scripting language. If I just double click this .cxc file, then it will load it up in ChimeraX and read those cropped files. As you can see, it's opening up the files here, and it's applying several steps to get a nice image, as you can see. So what's in that file? For each of these, so for example, on the CK reconstruction, it just opens and then it has to have the correct file name. It sets the size of the voxels. It sets a view orientation. It runs a median filter on that to smooth that out a little bit. And then that turns it from volume number 1 to volume number 2, so we can close number 1. And then for volume number 2, we'd make it red and set a projection mode. And then in this case, we hide it because I don't want to look at the carbon signal. But if you were to come down here and look at iron, that one is shown, for example. And you can do a whole bunch of different things depending on what you want to do. If you're interested in ChimeraX, you can learn that scripting language. Something which is very important is how do you set the thresholds for drawing these elements. So let me make this a little bigger. And then we're going to look here at the magnesium signal. So in this case, I would prefer to start with the unreconstructed magnesium K signal. So this is the magnesium K stack. And somewhere around the middle is the 0 tilt. So you have to look at the actual number. So this is 0 tilt right here. And if I rotate this around to 0 tilt, then I should be able to see these same outline for the magnesium features. Actually, I need to make sure that we can see the magnesium image as well. So here is magnesium, and I could set our threshold higher or lower depending. So here I've set it to make sense with the EDS view. And it's really worth your time to spend a half an hour or something going through the EDS maps as well as the tomographic reconstructions to make sure these thresholds are all correctly set one to another. And I'm also interested in if anyone has ideas about how to set more automatic thresholds that don't have a human bias introduced. So I believe this is an area where we will develop in the future and where something needs to be improved. But for the here and now, this actually works very well and gives quite a nice, meaningful result. All right, thank you for listening. If you have any questions, please email me and I'll respond. ZachG@berkeley.edu. And until next time.